case here, so basically we are discussing the backprop algorithm. So basically in this case, at first we have to calculate the value here, what are the outputs, and then we have to find the loss function, and then we have to backpropagate. So here to find H1, we have to like multiply W1 into I1. So this one into this one into this, and this weight into this, right. So if we calculate 0.15 into 0.05 here, then this value 0.2 into 0.1, and then this value is 0.35 into 1, this one is 1. So it will be like 0.3775, and then after you have pass it through this activation function, the output of that will be 0.5932. So you are just putting this value in place of net H1. Okay. So the final output here will be this one, 0.5932. Similarly, if we find for H2, this one into this one into this, and this one into this. So whatever whatever edges are there in the H2, we are taking the like multiplication and then summation, and then if we again take it through the activation function, then after the activation function we will get this output 0.596868884378. So this will be the output here, and this is the output here. Then in the next stage we have to again perform the similar thing. We have to multiply this into output of this into output of this, and this into output of this. So like just one, because this is not output of the previous layers. So if we do this, so the here the values will be 1.1059, and if we again pass it through the activation function, the value will be 0.7513. And similarly, if we calculate for this one, the value again will be 0.7729. Okay. So after this, we got the values here, we got the output values here and output values here also, but these are the labels. So ideally the output here should be 0.01, and ideally here should be 0.99. So we have got the output and we have the labels. So from this we can now calculate the loss function. So loss function can be calculated by this formula. So half into target minus output whole square. So target, so we have two output. Yeah.
Sorry to interrupt, but in the given figure,
Yeah.
the first layer, that is I1, I2 and 1, they have weights associated with them, that is 0.05, 0.10, isn't it? But in the middle layer, that is hidden layer H1, H2, H1 and H2 don't have any weights associated with them.
Yeah.
I
So,
mean, like,
okay. So this isn't really a kind of say weight. We can say this is at the input. Okay. So this is present in the data set. This is the input value. So in the next example, input can be different. And this is the, so here what would be the weight here, like we are getting the output here. So suppose in this case the values will be this one. So in this case, in the first case, because this input we have the values, we can just get the values here 0.05 and 0.10, but in this case
those are the labels. Are those the labels on the input, this 0.05 and minus 0.10 and 0.35?
these are the inputs, not labels are this. Okay, the output labels. 0.01 and 0.9. So what happens is that suppose you have a neural network and you have some weight, and these are the hidden layers. So this is kind of say fixed for this example, and you are calculating the hidden value here. So suppose we are considering it as 0.05, but in this case we will calculate the out H1. So this is 0.5932. So here it will be like 0.5932, and here it will be like 0.5968. So these things we have to calculate, it will not be given, and then we have to repeat. So in the next case, like O1, we have to consider this, like this one into whatever value we have obtained here. So here, yeah, these are the values, 0.45 into this is the value we have obtained here. So this is how we do it. in like for propagation, we are just multiplying by weights and inputs, and
For
for
the
expansion.
line going from H2 to O1, there is no weight given actually. Is there? Oh, that is 0.5
Yeah.
W7. H2 to O1.
No, this one is 0.445. This one is W6. Okay. So here.
Going from H2 to O1,
Yeah.
line from H2 to O1.
Yeah. H2 to
What is the
O1.
weight?
So this is 0.45, right? This one is W6. This one.
I thought the H1 to O2 is 0.45. No. What
Uh,
is H1 to O2 then?
yeah, H1 to O2 is like 0.50. This one is W7. Yeah.
Okay, okay.
Just
Very
like
nicely.
some leveling confusion. Yeah.
Yeah.
So then we got the yeah. You have any questions? Okay. So then we got the
Weight
outputs here.
vectors are the, sir, these weight vectors are the tunable parameters.
Which one?
These weight vectors
Huh.
means weight. In these hidden nodes, there are some weights assigned to each line. Is this the tunable parameters?
Yes. So these are the weights 0.15, 0.20, 0.2530, and here also these are the weights. So all of these are tunable.
Sir, if it consists of more than one hidden layers, then how will we calculate the tunable parameters?
Yeah, I'll discuss this in the next steps.
Okay, sir.
Yeah. So at first, like let's calculate the loss function here. So this is the kind of expected output 0.01, and this is the say the output we have got. So we are taking this minus whole square. We are taking the subtraction, then whole square, and then we are multiplying into 0.5. So we are getting this. So loss value here is 0.2748, and similarly loss value here is 0.02. Okay, and if we add them, it will be 0.2983. So this is the total loss with this error function. Okay, so with this loss, then we'll calculate the kind of say the backpropagation with this loss. Okay, so how to update weight 5? So basically we have to kind of calculate everything. Everything means we can update this weight, we can update W5, W6, W7, W8. At first we have to update them, then we can update them. So again there are, we can say this one is one layer, this one is another layer, and we have to calculate this thing first. So basically let's just consider here how to update W5. Okay, so at W5 we can calculate by this formula. So basically we have to find like partial derivative of total error with respect to W5. So how much the total error is changing with respect to W5. So how can we do this? Is there any direct way to perform the derivation? Is E total directly dependent upon W5? No. So E total, you can see here, this is the formula, right? So target output, it is not directly dependent upon W5, it is indirectly dependent upon W5, because output that is coming from W5, right? So how to kind of form a chain to find the E total partial derivative of E total with respect to W5. So we can do one thing, E total, suppose here, so error total, E total is like summation of these two, right? So we can do one thing, W5 here, so E total is summation, then E total what is the out where the W5 is going, it is going to O1, right? So we can try to do with respect to O1. So we have to find at first that what we are calculating error of 1 here, error of O1. So at first you are finding what is the partial derivative of total error with respect to what is the error here. Then we are multiplying it with respect to this one, like what is the output here and what is the before the activation function. So this one is the just derivation with respect to the activation function. Net O1, what is net 1 means like whatever we are getting by multiplying, and multiplying this into this, this into this, and this into this. Okay, and then out 1 means after performing the segment, after performing the activation. So basically, after calculating this, like we are taking derivative with respect to that also, and then we got this one like partial derivative of d net 01 and d w5. So basically, the thing is very not really very much complicated. So here we got the w5 and we want with respect to e total, but e total is not directly related to w5. So we trying to divide it in some way such that it is kind of related. E total is dependent upon w5. So e total is dependent upon out O1, this one, because you know e total we can do with respect to out O1, right. So we are trying to break it to out O1, and we know out O1 is dependent upon net O1 and net O1 is dependent upon W5. So this is the chain we are forming, and if we calculate these three, then we will get this value, right. So let's go step by step. E total with respect to d out O1. Okay. So E total value I think I have shown in the previous slide. So this is the E total, half into target minus output whole square. So we have two targets here and two outputs. So target O1 minus out O1 whole square plus target O2 minus out O2 whole square. Okay. So this is the E total value. If we take derivative with respect to O1, so you know this one is not related to this is not a function, this part is not a function of O1, so this will be 0. This one is a function of out O1, right. We have this one. So what we will do, this will come here, right. So 2, if we take derivative, it will be 2 into this whole value, right. 2 into half target O1 into out O1 minus out 1, and then it will be if you take x square, it will be the derivative will be 2x. So same is happening here, 2 minus 1, which is kind of like same. Now half into target O1 minus out O1. Then since this is we have taken with respect to this the whole thing, so we have to take derivative again with respect to all this. Okay. So this will be like derivative of minus out O1 with respect to out O1. So this will be like minus 1. So if we simplify them 2 into half, which is 1, 1 into minus 1 is minus, and here we get target O1 minus out O1. So this is the value of E derivative of E total with respect to out O1. Okay. So if we just put the value here in the previous step, target O1 we have calculated. So target O1 is 0.01, we have it is given in the data, and out O1 we have calculated. So this is the out O1 0.7513. So if we just put the values here, so this will be the output. This will be the value of this part E total with respect to out O1. So till now is it clear? Then I will also calculate this. So then we can find the value of this. So I hope it is clear to everyone. Okay, so I am going to the next part, out O1 into out 1 with respect to net O1. Okay. So out O1 formula is this 1 by 1 plus e to the power minus x. So x here is like net O1, and this is the derivative. So derivative of sigmoid function is like out like x into 1 minus x. Okay. So, here out 1 into 1 minus out 1. So, you know what is the out 1? Out 1 again we have calculated earlier 0.7513. This one is the out 1 into 1 minus out 1, this one. So, if we calculate this, the value is 0.1868. Okay. So, we had two part, we have three part equation, we have calculated this part, we have calculated this part, then we have to calculate with respect to d net O1 and d W5. So, net O1, how to calculate net O1? W5 into out H1. So, W5 into this, then W6 into this out H2 and B2 into 1, B2 is 0.60. Okay. Anyway, so if you take with respect to W5, this part contains W5. So, if you take derivative, then it will be like derivative of W5 with respect to W5 will be 1 and this will remain the same. Okay. And then like if we take the again the derivative with respect to whole thing, it will be like 0, like it will be 1. So, basically in this case, like you know, if you take this is suppose some value and this is suppose x. So, if you take derivative with respect to suppose 5x, the value will be 5, right. So, same thing here. So, we are taking with respect to W5 and W5 will not be there and out H1 will be the say value here. W6 and out H2, it is not dependent upon W5. So, value will be 0 and B2 into 1, this is also not dependent upon W5. So, it is will also be 0. So, derivative of net O1 with respect to W5 will be out H1. So, out H1 value we have calculated earlier and the value was 0.95932. So, again you will see there are three values here, three values we have calculated separately, and if we calculate and then if we just perform the multiplication, we will get this value E total with respect to W5. So, basically we got all the values here. E total by W5 is this output of this and output of this. So, if we multiply all of them, we will get 0.082. Okay. So, this is
why are we trying to update W5? Is it just for an example? Just randomly we are trying to update, you're showing how to update any one weight?
We have to update all the weights. So, for example, we are seeing W5 here, same we have to do for W6, W7, W8. So, all of these are
Not for W1 and W2, W3, W4?
Yeah, that will also have to do. So,
Okay.
all of them we have to do. So, yeah, so we got this value derivative of E total with respect to W5. So, if we multiply all these parts, we are getting 0.08. Okay. And how to calculate the weight then? W5 plus. So, this means like weighted weight of 5 on the next iteration. So, what will be this? W5 minus this is the learning rate and then we have to give this value. Okay. So, suppose, so what was the W5 earlier? W5 earlier is 0.40, right, and for just for we are assuming the learning rate is 0.5. Okay. And this is the value of this E total with respect to W5. So, earlier value minus learning rate into the derivative. So, if we calculate this, the value is 0.3589. So, this will be the new value of W5 in the next iteration. So, suppose we are giving a new example in the next iteration, we have to find a forward propagate with this value and then we have to back propagate also, but the values in the next iteration, the values will not be 0.40, the value here will be 0.35. Okay. And if you try to simplify this, okay, so what does this mean? E total with respect to out O1. So, this one is okay. So, E total with respect to out O1, this one is this value, right, minus target O1 minus out O1. So, we are just writing it here. sigmoid value, if you take the derivative, this is here out O1 into 1 minus out O1, and derivative of this one is out H1, right. So, even if you so this is the simplified equation. So, if you just put the values here, then you will get the exactly the same value, because you know this value we have just found it with this only, right. So, this is just the simplification of this equation. So, you can also calculate this calculate the same number with this equation. So, this is for W5, and you know W6, W7, W8 they are exactly the same, like you know W5 it is this into this into this, W6 it will be like it will be this into this, and just as we have calculated W5 we can calculate W6. So, here like for W5 it is like this into this plus this into this for like O1. Okay. So, with respect to W5 what do we need to change? So, sorry, suppose for W6 suppose, okay. So, W6 also here, so everything is same, right. W6 is also going to O1, so it will also the same, everything will be the same, but here instead of net O1 it will be like it will be net O1, but here it will be like W6. Okay. So, we will get some value, and if we do like 0.45 minus 0.5 into that value, then we will get this one 0.40866. For W7 instead of O1 it will be O2, because you know W7 is coming to O2, and for W8 also it will be like with O2, but the basic summation basic thing will remain the same. So, for W7 W8 it will be like d of E total d of O2 into d O2 out like out O2 and d net O2, then d net O2 into d W7, because you know 7 is going to O2 and 8 also is going to O2. So, in this case it will be like O2 in case of 7 and 8, and in case of 6 it will be everything will be the same. Instead here it will be like W6, because you know W5 and W6 both are going to O1. So, this is how we update the weights here. So, after updating, this will be the new weights. So, I think this weights in this layer is like you all understood. Then I will go how to update W1, W2 and W3, W4. So, I will just show one example of W1, but I hope till this point it is clear to everyone. If it is not clear, please let me know, I will discuss it again.
Can you just go through the important equations, the main equations used in this? Just I tried.
Yeah. So, I will also share the slides anyway, but okay. So, this is the you can say okay. This one you can write down. So, if you calculate this E total with respect to W5, and then if you put into this you will get everything. So, this is again for this neural network. If the network is different, the loss functions might change and the like multipliers might change. So, it is like you have to kind of try to understand what is happening in the network, and then how to propagate the errors. So, basically just as we have done here, we are taking the error, then we are taking derivative of the error with respect to error here, then with respect to the sigmoid function, then with respect to the like cumulative input here. So, that chain you have to kind of see on the network. So, maybe there can be more nodes also, instead of H1, H2 there might be H3, H4, anything can be there. So, that you have to kind of consider.
Like, where did you this minus of target O1 minus out O1 into out O1 into minus out O1 into, like, what is the basis for that equation which you have highlighted in blue color?
Yeah. So, you know, there are three kind of say numbers here, this one, and this one. So, we have calculated all three parts differently. So,
Okay.
if you go here, E total with respect to out O1. So, this is this value minus target O1 minus out O1. So, just putting that here, this value is this one out O1 minus into 1 minus out O1. We are
Okay.
putting here, yeah,
So, like, okay, yeah.
yeah.
So can you just go back to previous slide so that I can take down like what is the error function?
Yeah, yeah, sure. So, this is the error.
Yeah, this one.
Yeah.
E total is equal to half target Okay, got it.
Okay. So, then I will move on to the next part. So, you know, till now we have done with respect to the last layer W5 W6, right. So, if we do with respect to W1 W2, it is a little bit more complicated, little bit, because you know W5 is connected to O1, right, but you know W1 is connected to H1 and H1 is connected to multiple things O2 and O1, right. So, how to do this? So, if you consider this equation, okay, so we have to propagate both this like with respect to E01 and also E02. So, how to calculate this? So, this is the this is the thing we have to calculate E total with respect to W1. So, total error is what? Total error is this one. So, E01 plus E02, right. So, how to calculate this? So, yeah, hello, yeah. So, we have to calculate what? E total with respect to out H1. So, then out H1 with respect to the activation function, and then that into like dW1. So, basically similar to the previous one, we are calculating the error here, then we are E total into out O1, then we are taking the derivative of sigmoid, then we are taking the derivative with respect to the W5, right. So, same process we are following here. So, E total, we will explain the E total later on, but just consider it as a the cumulative error, total error here with respect to H1 here, then with respect to the sigmoid, then with respect to the W1. Okay. Now, the problem is that E total, it is not totally dependent upon W1 directly. E total we are calculating from E01, E02, which is again we are calculating from O01, O02, O2, O1, O2, not directly with W1. So, we have to make it, we have to expand it to so that it is dependent upon W1. So, here E total with respect to out H1. So, what is this? So, if we try to find a partial derivative of E total error with respect to out H1. So, we have to find in how many ways it is contributing to the error. So, it is contributing to the error via E01, so via this node, because you know we are taking the summation of the output here and output here, so error here and error here. So, it is contributing via O1 and also it is contributing via O2, right. So, this will be the error. So, with respect to O1, what is the like partial derivative of H1, and with respect to the H1, what is the partial derivative of O2. So, we have to calculate this. So, then again is EO1. So, EO1 is here. So, again we are focusing part by part. So, at first we have, so basically we have to calculate this. This is not calculatable easily. So, we are dividing it to these two parts. Then again we are focusing on this part. Okay, E01 with respect to out H1, E01 with respect to the out H1 here. So, how can you calculate this? Error 01 with respect to net O1, right. So, error 01 with respect to net O1, which is the here, and net O1 with respect to out H1. Okay. So, you can do anything, right. Here error 01 with respect to like you can say out H1, then out H1 into net O1, you can also, sorry, out O1 into net O1, anything. So, basically we are trying to break up here the loss functions, and we are trying to propagate it, we are trying to calculate the partial derivative of this with respect to this. Okay. So, we are basically breaking it up, error of O1 with respect to net O1. So, output here, and then output of net O1 into like with respect to this output here. Okay. So, you know this with respect to this we are unable to do directly. So, we are doing this with respect to this and this with respect to this, as simple as that. So,
What is, why is that H1 divided into net and out? What is net and what is out? Like
which one, which equation?
in that in the diagram, no, the circle H1 is divided into two hemispheres, net and out.
Yeah.
Two semicircles, net and out.
Yeah.
What is
So, net is basically before activation and out is after activation function.
that? Okay. Fine.
Yeah. So, then basically again we are getting two part here, EO1 with respect to net O1. So, EO1 with respect to net O1. So, this is also not calculatable directly, because here also we have get net and here also we have got out. So, it will be like with respect to out 1 and out O1 with respect to net O0. So, basically what we are doing here is that we are calculating error with respect to the output here, then with respect to the sigmoid like activation function, then with respect to this one output here, plus here the output here with respect to the like error here with respect to the output here, then with respect to the activation, then with respect to the this one. Okay. So, these two different errors we have to find, we have to take the derivatives and then we have to sum, perform addition. Okay. Because this is cumulative of this one and this one. So, if we calculate this d of E01 E1 and E out O1. So, error here with respect to the output here, if we calculate, we have calculated this earlier 0.7413. So, I will just show this one, E total with respect to, E total with respect to D out O1. Okay. So, this is the same 0.7413, this is the same as this one. Okay. This is the same as like 0.7413, because if we take a derivative with respect to this is not dependent upon this, right. So, like derivative of E01 with respect to out O1 is same as derivative of total with respect to out O1. Okay. So, this value is the same, and then d of out O1 into net O1. So, again we have calculated this out O1 net O1. Let us just find out O1 into net O1. So, this is 1.1868. So, again we are just putting the values here. So, we got this 0.1384. So, this is like E01 with respect to net O1. Okay. Sorry, with respect to net O1. So, net O1 is here. before activation. Okay. So, we got this, then let us find. So, this we have found, yeah. Then net O1, how to find net O1? This into this into this into this, right. So, W5 into out H1, W6 into out H2 and B2 into 1. This is the equation, and how to find with respect to out H1, we are just take derivative. So, something into W5. So, if we are taking derivative, only W5 will remain. This one is not dependent upon out H1, so it will be 0, this will also be 0 derivative. So, this value is W5 and W5 is 0.40. Okay. So, if we put it into this equation, EO1 with respect to net O1. So, this we have calculated here, it is 0.1384, we are just putting the value here, and W5 we are putting the value. So, we are getting 0.0553. Okay. So, this is the out O1 with respect to out H1. So, this one with respect to this one. So, we found a partial derivative of that. Okay. So, this is one part. Then again we have to find the same for this, with respect to EO2, derivative of EO2 with respect to this one, out H1. Okay. So, similarly, if we calculate this, it will be similar, like here instead of H1 out O1, it will be like out O2, but everything will be the same. Okay. So, everything here, like it will be if we take the derivative with respect to out H1. Okay. So, here we have calculated this here. Okay. So, now we are expanding this EO2 with respect to out H1. So, if we expand with respect to EO2, this will be EO2, this will be net O2, this will be net O2, and this will be out H1. Okay. So, again if we calculate those values, it will come to this one minus 0.019, and then so basically we need to calculate two values, this and this. So, this one we have calculated from here, and this one we have calculated from here. So, if we just add them, we will get 0.03. Okay. So, this one is the final derivative. So, E total with respect to out H1. Okay. So, total with respect to out H1, but can we really update W1 with respect to out H1? No, we have to perform with respect to W1. So, how to do that? So, again out H1 we are getting the value here, that partial derivative of out H1 we are getting, which is 0.03. But how are you getting that? What are the steps before that? We have taken activation here, right? So, we have to again take derivative with respect to the activation. Okay. So, out H1 into 1 minus out H1. Okay. So, out H1 is so this one was the output of this this layer. Okay. So, if we take this, it is like 0.2413, this value. Okay. And so, this is the derivative with respect to the sigmoid here, and then net H1. How are we calculating the net H1? W1 with this into I1, then we got this one into this 2, W3 into I2, like that. So, if we take the derivative, it will be W1 into something. If we take the derivative, this will be like, this will be only remaining, W1 will not be there. So, this one is the derivative, net H1 with respect to W1. So, if we put all this together, so we got derivative with respect to W out H1, then we have to find out H1 with respect to net H1, then we have to find net H1 with respect to W1. So, if we put all these three together, so this is the partial derivative up to H1, out h1. So this one is the value we are putting here. With respect to the sigmoid, this is the partial derivative, and with respect to the before activation, with respect to the W1, this is the 0.05. So this is the final value, partial derivative of E total with respect to W1. Okay. So this is the value. So how to update the weights? By weight we can update by previous value minus learning rate into the partial derivative. So here 0.15 was the earlier value, you know, for W1. If we go earlier, 0.15 was the value. So we are putting that here. Yeah, we are putting that here. 0.5 is the suppose the learning rate, and this is the partial derivative. So if we calculate the equation, it will be 0.1497. And same, if we just follow the same step for W2, suppose this is a W2. Okay, suppose this is a W2, then we have to again calculate with respect to the out H1, and then with respect to net H1, then with respect to W2. So for this case, everything will be the same. Here it will be W2. For W3, what will be the case? For W3 and W4, it will be like here, it will be like with respect to E total with respect to out H2 with respect to say net H2 with respect to W3 or say W4. So if we calculate by this method, then we can kind of calculate the updated weights. So you know, at first we are calculating the updated weights for this one, then we are calculating the updated weights for this one. So all of the weights are updated. So whenever we are giving a new example in the next step, we will use these new weights. So W1 will be this, W2 will be this, and this. Same for like these values. And so if you perform this step multiple times, at some point it is expected that it will converge, and it will kind of give very good prediction on the new inputs. So this is the kind of say basics of backpropagation. So so the example is little bit longer because you know there are multiple hidden layers involved here, but I think you understood the main point here. So if there are a weight which is going into multiple direction, we have to kind of take summation of them, summation of the partial derivatives on both the paths. So that is the point here when you are in the when you have like calculating weights, updated weights for something that is not in the last layers. So if you have any confusion regarding this method, please let me know. Then after this I will move on to like practice questions. Okay. Okay. If you have any question, just ask. For now, I'll show you some of the question. So suppose you have a trainable parameter and you have a neural network and you have a 3D input. Okay. So 3D means you have here we have two. I have two inputs, but in your case, suppose you have 3 inputs. Okay, and in the output here we have suppose 2 output here, but in this we are saying that we have only 1 output, and there are 4 hidden layers and each of them contain 10 hidden units. So there are no bias term. So the question is how many nodes are there. So can you calculate this? So you know in this case what are the number of nodes? The number of nodes are 1, 2, 3, 4. Okay. And but in this case I am saying that we are having 3D input. We have instead of 1 hidden layer, we have 4 hidden layer, and instead of like only 2 nodes in each of them, we have 10 nodes in each of the hidden layers, and in the output we have only one output. So, what are the number of parameters that we can update? Total number of parameters in this model. I will give you some time to calculate, then I will solve the question. So, if you have solved the question, please send it to the chat box. I will look at it. So, can you do this if there is only one hidden layer? How many of them will be there?
Sir, what does it mean? The 3D input regression on 3D inputs.
3D means you have 3 inputs. So, in this case, you have 2 inputs, but in this question we are saying that you have 3 inputs.
Okay, sir.
Yeah. So, any of you are solving, or should I just go with the answers? Okay, let's move forward. So, basically we have 3-dimensional input and 1-dimensional output, and we have 4 hidden layers, and each of them contain 10 nodes. So, this is the basic diagram: 3 inputs, 4 hidden layers, 1, 2, 3, 4, and finally we have a output layer. Okay. So, how many weights are there? So, this is the question. So, let us find out. In the from input layer to hidden layer, first one, from this node we are there is one edge to every node, right. So, 1 into 10, 1 into 10, 1 into 10. So, this is 10 plus 10 plus 10, there are total 30 nodes in this part. So, then first layer to second layer, there are 10 nodes here and there are 2 nodes here, and 1 to every, there are connection between every node to every node from this layer to that layer. So, it is 10 into 10, 100 nodes. Similarly, for here to here, this part, 10 nodes here, 10 nodes here. If we they are fully connected, means from every one to every one there is a edge. So, 10 into 10, 100 nodes are here. Third to fourth again, 10 into 10, there are 100 nodes. Okay. And finally here, so there are 10 nodes here, and every node is there is an edge to output. So 10 into 1, right? So 3 into 10 is 30, 100, 100, 100 and 10. So 300 plus 30 plus 10 is 340. So this is the total number of trainable parameters of this model, considering that we do not have any bias term here.
Sir, how can we write in general this?
Okay, so in general you can see this input into hidden dimension, right? First one is this. So I'll just write here. Input dimension into hidden dimension plus so how many hidden layers are there? 4, right? So number of hidden dimensions minus 1 into number of hidden layers. So basically then we have finally hidden So basically this is the kind of say generalized formula. So input dimension, we have to find this part at first. So input dimension into hidden dimension, this one, number of hidden layer is 4, okay. So and there will be 3 fully connected layers. So basically, you know, if there are 3 layers, 3 hidden layers, it will be like 200. If there are 4 layers, it will be 300. So the number of layer, the fully connected layer, fully connected edges between the hidden layers, it will be total number of layer minus 1, because we are calculating the fully connected layers between them, right. So if there are 4 layers, there are 3 in between connections. So that will be this number of hidden layers minus 1 into hidden dimension this into hidden dimension again this, and then finally hidden dimension is this and into output dimension. Output dimension is 1. So this is the generalized formula of this.
Okay, sir. Sir, if we consider bias, how it will change then?
Yeah, I will discuss bias in the next example. So similarly, this is the same example, but consider that we also have a bias term. So the we have calculated earlier that we have 340 a number of weights, but suppose we have another term called bias here. Okay, so what bias means? What every term, like in each of the node there will be another term added, except like in input layer, because input it is given, but in all these and these there will be another term, right. So what will be this? So how to find number of bias? So consider like this, there are one term in this, one term in this, one term in all of this, one term in all of this, plus one term in this, right. So bias, how can you calculate? We can do this bias, we can do like number, so number of hidden layers into number hidden dimension plus output dimension. So this is for bias, and weight we have calculated earlier, right? And this one. So if you add them, you will get the total. So 4 into 10, 4 is number of hidden layers, and 10 is the number of hidden dimension here, and 1 is the output here. So if we add them, 40 plus 1, 41, and the weights are 340 and total 41 bias. So total will be 381. So I hope it is clear. I will go to the next question.
Sir, can you go back to the slide?
Yeah.
Yeah, so bias means we have to just add that one, right, sir?
Yeah, we have, yeah, add that one.
Okay, sir. Thank you.
So not just one actually. So here we have 4 layers. So in each of the nodes we have a bias term. So we are calculating like this one into this one, this one into this one, this one into this one, plus some value plus b. Here also these 3 into the inputs and plus b plus b. So this is the bias value. So here we have 10 biases, 10 biases, 10 biases, 10 biases, and here also one bias. So 41 number of biases are there, and 340 is the number of weights, so edges here. So total will be 381.
There will not be any bias at the input layer, sir?
No, input layers there is no bias.
Hello, sir.
Yeah.
Sir, I have a doubt. Sir, I think bias factor is different for each and every layer. Is it like that, or for hidden layers it is same?
No, it is different for everything.
Yeah, because that activation function, it depends upon that, na?
Yeah.
So why here we are using 4 into 10 plus 1?
So this is we are saying that what is the number of biases. So bias is actually dependent upon node.
Yeah, this point. Feature actually.
Yeah.
Okay. Sir, I got it.
Yeah.
We are calculating only number of biases.
Yeah, number
We
of
are not
biases.
giving the value of bias.
Yes,
Okay.
right.
Thank you, sir. I was
Yeah.
confused.
Yeah. Okay, so
More than one output, then the bias will be plus one number of output. It will have to add the number of outputs, right? 4 into 10 into the number of outputs.
yes, right.
Okay. Thank you.
So this is the next question. It looks complicated, but answer is really simple if you think. So you have a okay. I think there is some question here. Okay, diagram if bias is added. Okay, let's do one thing. Yeah, Priyanka, you can.
Sir, what is the difference between that hidden units and hidden layers?
Okay, so yeah, I'll show the diagram in a bit. I'll just answer the question. So hidden layer means this one is 1 layer, 2 layer, 3 layer, 4 layer, and hidden units is in each layer how many nodes are there. So there are 4 hidden layers, and each of them we have 10 units. So this is called hidden dimension.
Both hidden dimension and hidden units are same, sir?
Yeah.
Okay. Thank you.
Yeah. So I'll show the diagram. Okay. I'll just neural network visualization. If you go with bias term. for hidden layer, suppose, and okay, I need to add another layer. Yeah. So this is a little bit complicated to look, but if you just consider here, we have 10 nodes here, and we are considering bias term for everything. So, if we just consider bias here, bias here, bias here, bias here, so this is the term. So, we are just taking another node here and we are adding the bias terms in everything. Similarly, for here, each of them has a bias term. Discard this. Suppose each of these, all this has bias term, and so we are considering 1 into this as a bias. Okay. Similarly, for these all have a bias, we are considering 1 into this weight as a bias. This one also same, 1 into this weight as a bias. Here also we have a bias, and that bias comes from this. Okay. This. So, you know how many of bias terms are there? There are 10 here, 10 here, 10 here, 10 here. So, 40 and 1. So, 41. So, basically instead of adding bias here, we have just like it is shown from this previous layer multiplication, but the idea is the same, that you will have a bias term for each of the hidden nodes, and we are considering that as a multiplication of 1 into that bias term. Yeah, welcome. So, Priyanka, you have a question, you can ask.
No, sir, no.
Okay,
Thank you.
fine, thank you. So, I will go to the next question now. So, this is the layer. So, in the previous example, we have shown that all of the hidden dimensions are the same. So, here also 10, here also 10, but here it is different. We have 4 here and we have 3 here. In the output, we have like 1. Okay. So, the question is, all of them are say hidden, all of them are 0. Weights are also 0, biases are also 0, and the input can be anything. So, the question is, what is the output here? If all the weights are 0, biases are also 0, and we have sigmoid activation.
Sir, is 0 the value or
0 is the weight, like weight of this is
okay,
also 0.
value of the
zero.
weight?
Yeah,
Value of the weight.
all the weights are 0, and all the
Okay,
biases
then
are,
output will be 0 because W. So when we are calculating the summation function W1 x1 W2 x2,
yeah.
so there we will get 0 because every time W1 W2 W3 will be zeros. and then these will be acting as inputs in the second layer, and go on, and finally we will get 0.
But there is an activation function, right? Sigmoid. So
Oh,
if you
then
give
it will
sigmoid,
be added.
yeah.
Yeah. Then activation function will be the value.
How much?
Sir, is it here?
Yeah, it is a sigmoid activation.
Means sine function.
Yeah, 1 by 1 plus e to the
1
power
by 1 plus e to the power minus something.
minus x. Yeah.
0.5.
Yeah. So yeah, 0.5 is the answer. So basically, what will happen? Suppose these are the weights. We don't care what is the like these are the inputs, and we don't care what is the input. Whatever the input is, we are multiplying by 0. So here the like net here will be 0. So suppose it is 100, it is 1000, whatever. We are multiplying into 0, it will be 0. Bias is also 0, so it will be it will also be 0. Okay. So the net here will be 0. If we give it to the sigmoid function, sigmoid of 0 is 0.5. So here it will be 0.5, 0.5, 0.5, 0.5. Okay. But even though it is 0.5 here, these weights are 0. These all the weights are 0. So 0.5 into 0 is 0. 0.5 into 0 0, 0.5 into 0 0, 0.5 into 0 0, and bias is also 0. So again the net input net here will be 0, net here will be 0, net here will be 0, and sigmoid of 0 is 0.5, 0.5, 0.5. So here also it will be 0.5. Again these weights are 0. So 0.5 into 0, 0.5 into 0, 0.5 into 0, bias is 0. So it will be 0 plus 0 plus 0 plus 0 is equal to 0. Again we have a sigmoid activation here. Sigmoid is of 0 is 0.5. So the final output will be 0.5. Yeah. So is it clear to everyone?
Sir, can you explain it once again?
Yeah. So basically in this question we are saying that all the weights here are 0 and all the biases here are also 0. So basically what we are doing here is, suppose we have some input here, doesn't matter what is the input, because we are multiplying it with 0, the output here will also be 0. So x1 into 0 is 0, x2 into this weight which is 0 is 0, something xn minus 1 into 0 if we take 0. So at this node everything is 0, but the thing is that we are passing it through a sigmoid function. Okay. So whatever the output here, like what is the net value here is 0, then we have to calculate the sigmoid of that. So sigmoid of 0 is 0.5. Similarly here also net will be 0, net 0, net 0, and if we calculate the sigmoid, it will be 0.5, 0.5, 0.5, 0.5. Okay. But in the next layer also we are saying all the weights and biases are 0. So 0.5 into 0, 0.5 into 0, 0.5, so 0.5 is the output here in all the cases, 0.5 into 0, 0.5 into 0. So if we multiply them and add, it will be 0, right? Here also it will be 0, here also it will be 0. So then again if we take the sigmoid, sigmoid of 0 is 0.5, sigmoid of 0 is 0.5, sigmoid of 0 is 0.5. But again in this case we are multiplying by 0, multiplying by 0, multiplying by 0. So again it will be 0, the net, this into 0.5, this into 0, this into 0, this into 0, and we adding them, it will be 0. Then again we are taking a sigmoid, so sigmoid of 0 is 0.5. So 0.5 will be the output here.
Clear, sir. Thank you.
Okay, thank you. So this is the next question. The perceptron learning algorithm is primarily designed from which task? Regression, unsupervised learning, clustering, linearly separable classification task, and nonlinear classification. So which one of them is correct?
Linearly separable classification task.
Yeah, right. So I think in the previous lectures also we have discussed this, like when can you use perceptron. So basically we have shown that we have two different classes, and if they are linearly separable, perceptron learning algorithm can try to obtain a boundary between those classes. if it is linearly separable. So the correct answer is this linearly separable classification task. Next one, so last layer of ANN. So ANN means artificial neural network is linear, and for which, and softmax for which. So this is the question. So suppose in this, and this is a artificial neural network. So linear means we have a value here, okay. So and then we have, in some cases we can have multiple values here, and then we can perform softmax over there. So the question is, in which cases which will be used. So linear means this one, a single output, and in softmax means there are multiple outputs and we are taking softmax over that. So kind of we can say, I think you have you know the softmax, because softmax is like if there are multiple outputs here, these divided by like summation of all these, this divided by summation of all these, and that will like so I will just show you the equation of the softmax function anyway. So yeah, so this is the value. So suppose we have multiple layers, suppose multiple outputs, and what we are doing is that we are taking suppose in the first softmax of first value, like first output will be e to the power that value divided by e to the power all the other values in that layer. So suppose we have suppose consider this is not there, okay, just consider this is as the like last layer, okay. So what will happen for softmax of this is e to the power this divided by e to the power this plus e to the power this plus e to the power this. So this is kind of, in softmax we try to kind of normalize the values between 0 to 1. So the question is like which one will be used for which case. So linear for regression and linear for softmax, or classification for linear and softmax for like classification. So what would be the correct options here?
Softmax will be used for classification.
Deepak,
And linear classification.
so I think it is classification and regression. Softmax is for regression and linear for classification.
No. So I'll tell you the answer, but that is not correct.
Thank you, sir.
So if you go to this diagram, so this is linear in the last layer, output layer. So when can this be linear? When you have a single value output, right? So when is the output value single? When you are regressing. So when we are predicting something, a value, maybe price of something. So in that case it will be like single value, right? In case of we are predicting between 3 or 4 class, that will be multiple values. Here also like will give that probability of this class is this class is this, like that. So in case of classification we will have multiple nodes in the output, but in case of regression we will have a single node, right? So linear means here we are getting a linear output here, just one. So this is the correct option here. So in this case, in case of regression it is linear, but in case of classification we can have multiple values, and to normalize them between like 0 to 1 we use softmax. Then next question. So the class.
Sir, even sigmoid we can use for classification, right?
Sigmoid, okay, the sigmoid will give a value between 0 to 1, right? So we can use for binary classification, but not for multiple class. Suppose you have 3 class, maybe say cat, dog and human, okay. So in that case you cannot really use sigmoid, but in case suppose cat and dog you can say that if more than 0.5 it is cat, if less than 0.5 then it is dog. This kind of thing you can do.
Okay, that means using sigmoid only two classification is possible, either 0 or 1.
Yeah,
Okay.
like if you give a kind of a threshold, that because you know sigmoid will give a value between 0 and 1. So, if you say more than 0.5 is 1 and less than 0.5 is 0, so that way you can do.
Sir, what will be the nature of graph of softmax?
Softmax will be like it will be also between 0 to 1, but it will be so suppose there are 3 outputs in the last layer, 3 output dimension. So, summation of all of them will be 1.
No, now for sigmoid we are having like in between 0 to 1, right? Now for softmax, how it will be, sir? We have to draw the nature of graph.
Okay, so I will just show you an diagram. Okay, so yeah, this is the diagram. Suppose this is the output value here, output value here, output value here. Okay, and then we are calculating softmax. Okay, softmax means e to the power this value divided by e to the power this plus e to the power this, e to the power whatever is there plus e to the power zk. Okay, so the thing is that after so suppose we have 3 output, after calculating the softmax we will get again 3 output. Okay, so in case of linear we are having one output, one output, and that is it. But in case of softmax, in case of softmax there are multiple outputs, and if we sum all of them, it will be 1. So, this is the property of softmax. So, you know, if we consider it as a multiple classification problem, we can say this is cat, this is dog, this is human, and this is like say zebra, anything like that. And we can say this will be between 0 to 1, and suppose P2 is the highest. So, we can say P2, this is the this example is say dog.
Okay, sir.
Yeah. So, next question, the class outputs of a classification problem with a NNN cannot be treated independently. So, I am saying that suppose you have a neural network like this, and I am saying that in case of this neural network you cannot treat this one independent of this. So, is it true or false?
Sir, these outputs are linked with weights. So when we are calculating summation function and every weight is being multiplied to some node value and so on. So should be independent or not?
It is not really independent.
Yes, sir. That's
So, because in this case, you know, you are calculating the softmax, and in the softmax equation, the P1 is dependent upon Z1, which is okay, but it is also dependent upon Z2, Z3, Zk, right? So, we cannot say P1 is independent of P2 or P3, because we are obtaining this from Z2.
yes.
Yeah.
Sir, and during back propagation, if we are going to adjust some weight, so we are going it layer by layer. So that is also the reason that these are not independent.
Yeah.
Thank you, sir.
So, this note you can view. So, output of the softmax activation function represent the probability, and if you add them, they must sum up to 1. So, if you think if one is increasing, other must decrease, because here Suppose it is 0.5 and everything else is 0.5. If it is 0.6, everything else summation should be 0.4 because everything should sum to 1.0. This is the probability. So they are not really independent of each other. Okay, next question. We have a simple artificial neural network. This is the input. Okay, so this is basically the bias. X1, X2 are the inputs, and hx is a function. So if x is greater than 0, then it is 1, and if it is less than 0, that means the output is 0. So this is a function. So the question is, which of the following logical function does it compute? So the question is like, if 0 0, what would be the output? If 0 1, what would be the output? 1 1, what would be the output? And which then based on input and output, what would be the function? XOR, NOR, NAND, and what?
What was the answer of the previous one? The class outputs of a classification problem with ANN cannot be treated independently. Oh,
Yeah, due to softmax.
Okay.
Sir, is it AND gate?
Can you explain why?
Sir, because in AND gate we are combining two inputs and finally getting A plus B like that. Na?
So AND gate we are getting A plus B. Okay, so in AND gate, in 0 0 we got 0, 0 1 we get 0, 1 0 we
Yes,
get
sir.
0, and 1 1 we get 1. So
Right.
is it happening here? Can you verify? I guess it is happening.
Sir, actually I had gone through the diagram only.
Okay.
Yeah, not through the
Yeah,
function.
yeah. I'll show you the solution. So I'll calculate every steps here. Suppose these are the possible values, right? So this one is always 1 because this is bias, and x1 x2 are the inputs. So what can be the possible values? 0 0 0 1 1 0 1 1. So at first we are adding the bias, then 2 into x1, because 2 into x1, so 2 into x1 is 2 into 0, which is 0, 2 into x2, 2 into x2, so this is also 0, so it is minus 3. Minus 3, if we give it to each function, it is less than this is coming under otherwise, so otherwise means it is 0. Next one, minus 3 plus,
And is the correct answer.
yeah, right. So minus 3 plus 2 into x1, x1 is 0, then plus 2 into x2, x2 is 1, so it is 2. So if we add them, minus 3 plus 0 plus 2 equal to minus 1. So again minus 1 is also it is not greater than or equal to 0, so it is 0. Similarly here also minus 3 plus 2 into x1, x1 is 1 here, so 2 into 1 is 1, here it is 0. So if we add them, minus 3 plus 2 equal to minus 1, and again it is coming under otherwise, so it is 0. Finally 1 1, so minus 3 is the bias, 2 into 1 is 2, 2 into 1 is 2 equal to 4 minus 3 is 1. So if it is greater than or equal to 0, it is 1. So it is greater than or equal to 0, so it is 1. So 0 0 is 0, 0 1 is 0, 1 0 is 0, and 1 1 is 1. So this is only coming 1 when both the inputs are 1. So this is we can say this is a AND function, because the same thing happens in AND function. If both the inputs are 1, then only it will be like 1. Okay. So is it clear to everyone?
Yes, sir.
So
Yes, sir.
so if the step size in gradient descent is too large, what can happen? So
For overfitting.
Overfitting.
Wrong.
Modeling not convex.
Yes, model will not converge. Option 3, we can reach maxima instead of minima, not necessarily. So I'll show you with the diagram. Okay.
The model will not converge means it is underfitting, right, sir?
Yes, it's underfitting. So this is the diagram. We are saying that step size. So if we are taking large steps, okay, suppose we are here right now, okay, and the global minima is here, right, but instead of going, so we have to do what, we have to come this side, right. So right now we are here, gradient is here, so we have to come this side, right. We have to jump there, this side, but what we are doing is that we are jumping way too much. So if you are jumping way too much, what will happen? We will come to this side here or this side. The main point is like we will just cross this. We are coming here. Then we are thinking that okay, the loss function is on the left. We should go left. But then again we are taking a long jump. So we are getting here. Then we are thinking no, the global minimum is on the right. So again we are taking a long jump. We are getting here. So we are never reaching to let's say global minima here. We are then again jump here, then jump here. This will continue. Okay. So we are not actually going to global minima. So this is not converging. But if it is learning rate is small, suppose we are initially at here, we are considering that yeah, we need to go right, but let's not take very large jump. Let's go slowly. So we are taking a slow step. Then we are thinking yeah, we are still we need to go right. So then again let's take a small step here. Then again we are thinking yeah, again we need to go right. Again taking a small step here. Again here. Finally we are reaching here. So if it is small, then we can reach the say minima. But if it is too large, then we can overshoot the minima and kind of roam around on other. We may not reach minima by if the it is too large. Okay. So the correct answer is that model will not converge because it is never going to global minima. So it is possible it is possible that suppose we are taking a step from here and by chance we are just reached here. It is also possible, but most likely thing that which will happen is that it will overshoot this, and like it will never actually reach the minima, which is the most likely scenario. But it is not that a model will not converge at all. It can happen, but it is very unlikely. So it can happen that we are taking a large step here, but by taking a large step we are going here, then we are coming here. It can also happen that by chance we are meeting at this point, but generally it will overshoot this point. Again we are taking large step, overshoot this point, again large step, overshoot this point. This will continue on happening. So it will never go to this point.
So this presentation will be available on the site, right?
Yeah. So you know the presentation. There is a spreadsheet for the presentation and YouTube link. So you have access to that. So okay.
Yes.
Okay.
That is under ask a question or under announcements.
No. I'll show you the link.
Okay.
Okay. So this is the your course.
Yes.
You go to here problem solving session.
Okay.
And from recording you go here, you have this, click here. So you will get a spreadsheet. So this is for my
Okay.
I will update the link here, and also in this folder if you go, you will find the slides. I will upload the week 5 here after
Okay,
the
thank you.
session. Yeah.
Thank you, sir.
Okay. So, okay, this question, let's move on to the next question. So, suppose you have a neural network and you are getting significantly different values of loss. So, suppose the weights are something, you are initializing the weights on something, the loss is 3, but in the next step you are initializing the weights, but loss is instead of 3 it is 30. So, there is very large difference. So, what can be the problem? So, based on different initializations, you are getting different loss functions. So, what can be the reason?
Different initialization means what, sir?
Suppose at first, suppose you have a neural network and like this, suppose this weight is 0.1, 0.2, 0.1, 0.3, something like this. So, this is one initialization, because you know you are doing, at first you are doing it randomly, right, the weights. Then in the next step, suppose it is 0.3, 0.2, like that. So, I am saying that at first you are training the model, at first you are initializing the weight randomly, you are training the model and you are getting some loss function. Then in the next, then again you are discarding the model and again you are initializing the weights differently. Suppose at first it was 0.1, now it is like say 0.8, it was 0.3, it is like 0.25. So, weights are different, and then again you are training the model, but at the first time you got a loss function equal to 3, but now you are getting loss function equal to say 25. So, huge difference. So, what can be the reason for that?
Maybe because of overfitting.
But if it is overfitting, suppose, so if it is overfitting on one weight, it should also, it can also overfit on the other weight, right? Suppose like overfitting means everything is coming to here perfectly, like this is the loss function, lowest loss, right. So, if it is overfitting, so in both the cases the loss will be the same or very similar, but we are saying that it is loss is very different.
Sir, incorrect activation function.
But we are actually using, so we are using same neural network, right. So, even in the first initialization, we are using the same activation function as the second neural network. So, if it is problem for one, and that should be the problem for the other also, right. So, why is it doing better in one, but doing worse in another?
That fourth option is given, no, sir, but we won't set minima, right, sir?
Yeah, we won't set minima, but the model will try to find the minima. Okay, let me answer the question. So, answer is multiple local minima, but I will explain with the diagram. So, how this is?
Sir, initialization means that with the weights that we apply.
Yes, like what are the initial weights? So, you know, okay, what are the so you have a neural network and you can suppose this is on initialization 0.15, 0.20, 0.25, 0.30. So we are basically initializing it, right? So you are randomly assigning the weights at first, then we are updating. Instead of 1520, we could have also done 0.55, 0.39, like that. Anything we could have done, right? Because this is randomly done at first. So we are saying that if we are doing 1.5, 0.15, 0.20 and this setting, we are getting loss of 3 after training. But if we are doing like 0.99, 0.74, suppose 65 here, 0.10, like that. So different set of random weights, we are getting loss value very different. So the solution is that we have multiple local minima, and how can we say that? Suppose with this value, with 0.1520, this set of values, suppose this is the global minimum, okay. Suppose with this loss value, okay, we are here with these weights, with weights that are given in this slide. We are here. So from here we are going here, we are going here, then ultimately we are reaching here. So the loss value is suppose 3. But suppose this is different, the initializations are like 0.30, 0.25, like this. In this case we are jumping here. So what will happen here? We will think that minimum is left, but actually minimum is the right here, right? The lowest point is here, but we will think, we do not know about that. So we will think that minimum, if we go to the left, we will reach the minimum. So we will come here, come here, come here, and here. Then we will think that left also there is higher, right also is higher. So this is the minimum, and here we will stop. Similarly, if we initialize differently, suppose here we will think that minimum is here, so we will come here. Here suppose we are initializing, we will think that minimum is on the right, so we will go here, we will go here, and we will reach here. So basically all these 1, 2, 3, 4, they are local minima. So what is happening when we are initializing something? Initially if it is here, then it can reach global minima. If it is here, it can reach this local minima only. If it is here, it can reach here only. If it is here, it can reach this only. So depending upon where our initialization is, we can reach multiple local minimas here or here or here, and depending upon that, that will be the loss function. So maybe if here the loss function is 3, if it is here loss function is say 7, here 10, here say 25, like that. So if we are reaching here, we do not have any knowledge that this exists or this exists. So we are getting stuck at here. So that is why the losses are higher. So because there are multiple local minima here, here, here. So depending upon from where we are starting, we can reach at any of this point, and depending upon that, our loss function will vary. So I hope it is clear to everyone. Okay, local minima and global minima. So in this example, suppose you are here. So this is your local minima. Suppose you are here, this is your local minimum. So by local minimum, what do you mean? Suppose this is the minimum if you consider this part. If you consider a box here, this is the minimum. But if you consider the whole diagram, this is not the minimum. So within a certain range, we are getting a minimum value. So this is called local minima. But global minima means within the whole loss space, okay, whole thing, there is only one place where we are getting the lowest value. So it is lowest here also. If we consider the whole diagram, it is also lowest here. So this one we call global minima. No matter wherever we take from the diagram, the lowest point in the diagram is here. But in this case, you can see, if we consider within this portion, this is the minimum. But if you consider the larger portion, the minimum is not this. Minimum is this. So if again if we consider this this thing, if we consider this range, minimum is this. But if you consider this larger range, minimum is not this. But if we consider any range, involving this range or this range or this range, the minimum will be this. So this is called global minimum, and all these are local minimum.
And how about global maxima and this local maxima?
Okay, so in this case, this is the global maxima, because this is the highest point, and no matter where you take, this is the highest. Here, this one is the local minima, local maxima, local maxima, local maxima. So suppose you are here, okay. Suppose you are here, and you want to reach the maximum. You will go here, and then if you go left, you will think it is lower. If you go right, you will think it is lower. You don't know that there are other higher points, right? So you will get stuck at here, right? So if within this portion, this is the maximum, but if you consider a larger area, this is not the maximum. So that is why you can say this is local maxima, but in the whole diagram, this one is the global maxima, because from whatever we are compared with, this is the highest. So yeah, you can see this diagram. This is the global maximum, the highest point, and this is local maxima. This is again local maxima, and this is local minimus. Yeah. And this is the lowest point, so this is global minimum. Optimal minima here, like so suppose you are trying to find the lowest point, okay. So what would be the optimal here? Optimal means where the like loss function is the lowest, and loss function will be the lowest in global minima. So optimal minima is just like global minima. Yeah, you can search the diagram also. Yeah, like if you are trying to minimize the loss function, at this point it will be like global minimum, and here it will be like optimal loss. So global minima is the optimal minima. Okay, so if you have any question, please feel free to ask, otherwise I'll end the session.
Sir, week 4 assignment problems, I am not able to do it.
Okay, so assignment, I think week 4 assignment already submitted, right? Already deadline is over, right?
Yes.
Yeah, so there will be an official answer solution within maybe 1 or 2 days. Like we'll upload.
The answer is there, by solution, how the solution comes?
Yeah. Solution will upload a PDF with explanations. So in the week 3, up to week 3, I think already uploaded here. Week 2. Okay, so week 3.
Where you uploaded, sir?
Yeah, so week 3 you can see week 3 solution.
Okay.
Yeah. So if you go to the solution, you will get in PDF. So in the PDF, there are explanations why, and with equations and everything. So week 4 it is not done yet, but it will be done.
Okay.
Yeah. Okay. So thank you everyone for joining.
Sir, sir, initializing the neural network weights, it should be a constant value.
It can be constant. It can be not be constant. Like it can be anything. You can do it randomly. You can also initialize with 0. But depending upon situation, it can like. So suppose if you initialize with 0, it can take a long time to converge. So generally it is done. So there are actually many different algorithms to initialize the values, so that we can train the model quickly. So in the later lectures, later weeks, we'll be able sir will cover those, so you can watch those. What?
Okay, sir. Can you explain the map and MLE related problems?
Okay, so map and MLE, I think they are large topics, so I think it is covered in the lectures. So you can.
Sir, assignment is about the problem, sir, not the theoretical questions of MLA.
Okay, but yeah, assignment actually I'm not allowed to discuss because assignment.
No, you should solve the similar type of problem of MLE and MF so that we can solve the problem of assignments. It will help to solve the assignment. Otherwise, how can we solve the assignment? In the video also, the problem is not solving. No?
No,
They're
no.
only discussing about the theory and
Yeah,
equations.
from the equations only in the video, you have to find the solutions. So in the videos, there are equations are written. Okay, so use those equations only. In this assignment, there is nothing which are not covered in the lectures.
Sir, I after solving week 4 assignments also still I have problem with the X or
Which one?
X or gate.
Week 4.
What is it all? Yeah.
Which question?
Sir, I think about 2 to 3 questions were there in week 3 and week 4 also.
Okay,
based
so
on
yeah.
based
So
on XOR. So I just want to know that like how now in the week 5 problem you have solved one sum solve and gate. So can you please show what exactly is XOR?
XOR. Okay,
Yeah,
so
the truth table
okay,
for
okay,
XOR.
okay. Yeah. Truth table for like a XOR is if any of them is 1, then it is 1, but if both of them are same, then it is 0. So this is the XOR gate. Okay, so 0 is 0. Only one of them is 1, so it is 1. Only one of them is 1, it is 1. And if both of them are 1, it is 0. Draw graph for AND. Graph means truth table, you know, but graph. Okay, and graph I can draw. Let me share it. Okay, suppose you have this one is suppose x1, x1, this one is suppose x2, this one is 0, and this is suppose 1, this is 1, this is 0 for both the cases. So AND graph means if the value is 0 for x1 and value is 0 for x2 also, then this will be 0. So suppose we are representing 0 with this one, because you know there is 0. So let's just do it 0 only. Okay, so this is 0 here, again 0, this is 0 and this is 1, so again it is 0, 1 0, it is again 0, and this is 1 1, only here it will be 1. So if we want to separate it by something linear, we can draw a line here, all the zeros are on this side, all the ones are on this side. So by this we can do.
Which link you have shared in the chat?
Okay, like this is for just the diagram. Okay, you don't need to see that. This one.
Sir, you should more focus on solving, sir. As it is a problem solving session, so you should more focus on problem solving.
Yeah, yeah.
Because the
So
videos also you cannot ask something or anything related
yeah,
problem.
sure. Like I can give more problems. That is not an issue, but I can't really give solutions. Like not, I can also discuss very similar solutions to the assignment.
Not very similar. So, this topic related problem you can solve. So,
Yeah,
you are discussing only theories, so it will not help to solve the assignments. Problem solving session mainly done for the assignment solution, problem solution,
yeah,
because theory is also there in the video lectures.
yeah, yeah. Sure, sure. I'll take it into note. So thank you, everyone. We'll meet next week then.
Thank you, sir. It was a good session.
Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.